For those of you already here, we're just going to get started in about 2 minutes or so. All right, I think people are slowly trickling in. But yeah, let's go ahead and get started on Unit 4 of Rose's 2021. So it's our great pleasure to be able to have Professor Eileen Martin present today's lecture on the topic of distributed acoustic sensing. Professor Martin has really been pushing the field of seismology in the context of distributed acoustic sensing forward by pioneering its use for a very wide range of applications, and also by using some really novel methods to analyze unique data sets that DAS yields. As a brief introduction, Professor Martin completed her PhD at Stanford University on imaging and characterizing the subsurface with distributed acoustic sensing. Professor Martin is currently an assistant professor in the math department at Virginia Tech, and will soon be moving to the Florida School of Mines to serve as a professor in both the departments of geophysics and applied math and statistics. So without further ado, please take it away.
Great, thanks very much. And nice to see all of you today who are calling in. We'll go ahead and share my screen. So I'm going to be talking about a technology today called distributed acoustic sensing, which has actually been around for a couple of decades in other fields, especially for defense or infrastructure monitoring, but has really only made its way into geophysics in the past decade or so, maybe 15 years. I would say more like 10 years. So we're going to look at what is distributed acoustic sensing. Why do we use it for different geophysical scenarios? What's it really measuring? How do we actually get DAS data if we want to work with it? And then we're going to go through a Jupyter notebook where you see how to read some public DAS data, how to visualize it, get a little bit of a feel for what it's like. And we've got some exercises for you to work on this week. So when we're looking at what is distributed acoustic sensing, let me move my Zoom thing. Okay, so when we're looking at what is distributed acoustic sensing, it actually fits into a bigger category of technologies called fiber optic sensing. So with fiber optic sensing, you have an optical fiber cable. This might be a single mode cable or a multi-mode cable, depending on the technology that you're using, but it's basically the same kind of stuff that you would use for telecommunications. And with that fiber, you don't just want to transmit your data from one point to another, but you actually want to be able to use that cable itself as the sensor, in addition to being the way to transmit your data. So all of these technologies, or at least many of them, have a setup where you have some kind of optical interrogator unit. Then that interrogator unit is going to be sending light pulses with a laser into this fiber optic cable. And based on either how the light scatters through the fiber or scatters back from different points on the fiber, it's going to interpret different parts of that optical signal to tell you something meaningful about various physical quantities. So this could include things like temperature, which is called DTS sometimes, or distributed temperature sensing. This can mean static or basically low frequency or slow strain, which is also referred to as DSS, distributed strain sensing, or it could be something like distributed acoustic sensing, which is really recording something like a dynamic axial strain rate or strain. And so that's what we refer to as DAS. And depending on how the optics are set up and which parts of the signal are being measured, it's going to tell you about these different physical quantities. So I'm just focusing on DAS for this talk. So a simple model of what's happening with DAS is, as you go into that interrogator unit, there's sort of a couple of pieces going on. So you're basically probing a fiber with a laser. So you've got to have laser control to send out these pulses. Then that laser light is going to propagate along your fiber optic cable. It's got various impurities in it, differences in density, differences in the material, things like that. And at every point along this cable, you're going to have a little bit of energy, some small percentage that gets scattered back towards your interrogator unit. And a lot of your energy is just going to keep going, traveling further along your fiber optic cable. As you get far enough away, eventually you start to get very little light actually getting to those faraway points. But we can easily go for something like kilometers, tens of kilometers, depending on the technology, sometimes hundreds of kilometers of fiber before we can really stop using that light signal. So that lets us cover really large distances with just a single fiber optic cable and just a single power source for our instrument. So once this light gets to all of these points and it scatters back based on Rayleigh optical backscattering, that light is going to eventually travel back to our interrogator unit. And a different part of the interrogator unit is actually going to be recording basically a very fast time series of what are those photons coming back. So we've got this tiny little, or very fast little time series of our photons coming back with that backscattered energy. And at any of those points in time when the light was coming back, we can say that based on the time for the light to return to the interrogator from the point that it scattered off of, so a two-way travel time, and based on our known speed of light in optical fibers, we know what our distance was where that backscattering occurred. So that means that every point in this little time series that we get back, we can track to a particular location in the fiber. And let's say if we've got some vibration source at a particular point, if we were to ping this fiber many times repeatedly, and we were to see that that point in our very fast little time series here were to be getting stretched or compressed a little bit or just varied in some way, we would be able to infer that somehow that path over here is getting stretched or compressed. So we would then be able to know that the fiber was being vibrated at that point. So that's kind of the basic simple model of how DAS works. There's a lot of other details on whether you have a double pulse or whether you're doing some sort of interferometer on this processing side, how you're doing that photon counting, how you're gating up a signal, but those are probably beyond the level of detail of what we need to just get started understanding our data. So, okay, once we get that signal that comes back, there's a few different parts to it that we need to sort of understand. So first of all, we might get this kind of time series like I was talking about with our light, where we want to be able to probe our fiber multiple times very quickly. Maybe we probe it thousands of times per second. So we've got basically a 3D axis of, all of these different signals that we're measuring, where we're looking at our photon intensity along our vertical axis here. We've got which time we're probing our fiber along this axis that goes kind of in and out of the screen. And then left to right, we've got our sort of fast axis. And that's basically what's the distance along the fiber at which those photons had to travel and come back. So in our slow axis, that's one ping of the fiber to the next ping. There's a limitation there. So we need our pulse to travel all the way to the end of the fiber and back. So if we have a really long fiber, that actually gives us kind of an upper bound on what's the highest sampling rate we can collect with our seismic data. And in particular, that's going to affect what is our Nyquist frequency for our time series that we collect at every point along the fiber. Then looking at this fast axis here, we have to figure out how are we going to break this up along the distance along the fiber. So how do we break it up into smaller channels? So each one of our channels is going to be broken up. Typical distances might be something like 1 meter, 2 meters, maybe 10 meters between channels. And that's basically saying what's the distance from the beginning of where we start cutting our signal to the beginning of where we start cutting our next part of our signal. So that channel length is basically what's the distance from the beginning of one measurement to the beginning of the next measurement. But each of those measurements is not just a single point. So it's not like with geophones or seismometers where you just have a single point measurement, but this is actually measuring what's our average extension or compression of the fiber along a certain distance. And we call that distance our gauge length. So that's kind of looking at what's the distance over which we're averaging our measurement. And that's a concept that shows up in a lot of fiber optic sensing technologies, not just DAS. And again, that channel spacing is just the time between our subdivided measurements, which corresponds to a space or a distance in space on our fiber. So I might have something like 1 meter channel lengths. So 1 meter between each of my different measurement distances, but I might have like a 10 meter gauge length. And so I might have many channels that actually overlap the same subsets of the fiber. So that's something that oftentimes gets a little bit confusing when people are first working with DAS. Okay, so we've got some basic idea of what DAS is and how it operates, but why would you actually want to use this? Well, let's look at some of the applications. So for the past decade, even 15 years, DAS has been really used to lower costs in oil and gas and to improve reliability there. So here's an example from just 2013 of some microseismicity detection at an unconventional oil and gas reservoir. So fibers were deployed underground in a well. They could fit into these very small well spaces, and they could actually record all the seismic data while oil and gas was being produced. And so that allowed this company, Shell, to be able to sort of detect any potential safety issues, to monitor the efficiency of microseismicity that was happening while they were actually producing. This is also, they also put a lot of money into investing in this technology and improving it because of the issue of needing to have 4D repeatable seismic imaging. And so that means when we're doing 4D, we want to do seismic imaging in 3D in space, but we also want to be able to repeatedly do that imaging and to track very small changes in our seismic velocities that are tied to things like fluid saturation or maybe even geomechanical stresses. So here's an example of just a vertical well, a VSP type of imaging, vertical seismic profiling. And here's an example that was offshore in the Gulf of Mexico with 2 wells that both had fiber in them that was able to do sort of a larger area offshore. Some people are concerned about certain limitations of the fiber optic technology as far as just being sensitive to certain directions of our waves. So there have also been a lot of investments in developing new types of setups for our fiber optic cables. So things like making cables that sort of wrap around a little bit so that they can actually stretch and extend in different directions and be sensitive to more types of waves. So that's another thing that's being developed in that sort of oil and gas space. But it's also a really appealing technology for those of us that work more in the space of infrastructure, or engineering, or near surface geophysics. For many of the same reasons. We want to be able to put sensors in tight spots that we couldn't fit before. We want to be able to cover long distances with high resolution. We want to be able to leave our sensors in the ground and not have to pick them up between each of our repeated experiments, or we want to be able to leave them there just to collect noise for a long time. I work a lot with passive seismic data, and for me to just leave a sensor out and forget about it for a while it collects data is great, as opposed to traditional sensors that might require you to go out and do regular maintenance, maybe swap out batteries, maybe pull data off of hard drives, those kind of things. There's a lot less of that with the DAS technology. We also have a much lower cost per additional sensor. Now, these fiber optic interrogator units are not cheap. The costs have been reducing drastically over the past few years as more companies have started to sell these systems. But really the real addition or the real cost savings is when you have extremely long distances, tens of kilometers of distance that you would not be able to afford covering all of that space with nodes at nearly the same density. So for us, that's a real win. Also, if we're trying to do seismic studies around infrastructure where people live, we don't have to worry about people stealing fiber optic cable that's just under the ground, maybe even an existing telecommunications infrastructure, because that's already secured. So it's different than when you take out a node deployment, let's say, or a seismometer, and you need to make sure that it's really secure. Instead, we just leave out our fiber optics. They're pretty cheap, about $1 a meter. If they did get stolen, it wouldn't be a big deal, but really, it's pretty secure. There's also a lot of emerging applications of using passive seismic data with just existing, what we call dark fiber optics. So these are fiber optics that were installed for telecommunications. They aren't being used necessarily because a lot of companies over-install their fiber. So they install many fibers at the same time in the same location. And we want to be able to use that dark fiber that's being not used currently just for science. So we want to be able to do things like imaging for earthquake hazard analysis, maybe even integrating these into early earthquake warning systems. We want to be able to do things like induce seismicity, location, and detection at a community scale. I heard that University of Oklahoma is doing some experiments in that space, which is exciting. And also detecting infrastructure problems. If you just have something like a broken water main that could lead to a sinkhole, if you have potholes in your roads, if you have railway misalignments, being able to see vibrations along your infrastructure can be really helpful for detecting and maintaining that infrastructure to be safe. So here's an example of an experiment that I led in grad school that was basically 2.5 kilometers of fiber deployed underneath the Stanford University campus. It ran for several years with, it's about 600 meters across at its longest and made this little sort of figure 8 shape. It's about 600 sensors or a little more than that. And I think we only had to do real maintenance on it maybe one time. It's pretty limited as far as how much time I had to spend in the field. It was pretty easy after the initial installation. So we had fiber optic cables that were pulled in our existing telecommunications conduits there, although newer experiments have allowed us to be able to use just existing fiber optic cables. And all those cables were 1 to 2 meters underground. So by having these dense arrays in urban areas, something that's really helpful is that we were able to see things like over time, we had a lot of different energy sources over a couple of years where we would have higher energy during the winter months, lower energy during the summer months. Weekday and weekend trends were visible. So here's just 1 month of data that was collected there, just looking at spectra of them. And you could see these kind of 5-day-a-week patterns from our anthropogenic noise in the area. And many of you who saw seismology papers during COVID may have seen similar plots, but something that's really cool once you've got these very dense arrays where we had 600 sensors here was that we could look at not just the values at one location, but we could really pinpoint at different locations how variable these data were. So just looking at 1 week of spectra from a channel up here that was by a busier road, and then a channel over here that's just in a pedestrian area, we see quite different spectra. And so up by the road, we see spectra that are really dominated by our vehicle traffic. But down here, where it's just a pedestrian area, it's more dominated by things like there's some from people walking around, maybe bicycles. There's a lot of these horizontal stripes that are more tied to things like our plumbing or our air conditioning systems. So yeah. And we can also look at just the entire array of data. So many people in seismology like to look at wiggle plots where you have a single sensor and then you look at just what are the amplitudes of that sensor over time. But with these dense arrays, it's really hard to make sense of those kinds of wiggle plots. They get pretty crowded pretty quickly. And so we tend to look at our data with these raster plots that are more commonly used in exploration geophysics. So Here we've got our fiber, it kind of wraps around this way. And what we've got is that we can actually look at every single channel and plot out against every single point in time over 10 seconds. What is that strain or strain rate value that we're measuring there? Here it's a strain rate. And so we can see things like a car driving, we can see a construction pop in a busy road. And I see one of the questions in the Q&A about if we can retrieve directional information from DAS. So I'll just point out that up here in the corner of the array, we've actually got this construction pop here corresponds to this construction, it corresponds to this construction site down here, sorry. And so when you have these kinds of corners in your array, you can actually start to do things like beamforming, where you start to figure out what direction that source is coming from based on how that move out is happening there from the construction site, if you know where that source is coming from. So Samara, hopefully that gets to your question there. And I see another question about the frequency band that's covered. So here, these cars, I'll go back to this plot. So this is showing a lot of energy between mostly about 2 hertz or so and about 25 hertz, but the 25 hertz cutoff here that's shown is really just based on us having a Nyquist frequency set that way, because we wanted to use relatively low frequency data for this particular experiment so that we could keep our data quantities manageable. But actually, there is a nice paper, there's one by Nate Lindsay and one by Patrick Peitz, where they talk about what's sort of that overall frequency band where your phase and your amplitude are reliable. And at least in the Peitz paper, it was something like 16 or 17 octaves worth of reliability. It's extremely broadband compared to your typical geophone or seismometer. Good. So some of the examples of why we would want this kind of density, in addition to just sort of being able to process different kinds of noises and being able to just know that those noises are happening, is that we might want to do things like near surface imaging. So I did some ambient noise interferometry there, and to be able to see these kind of fine details and interpret what kinds of waves we were seeing, we needed to be able to have this really high density in our sensors. We also needed to be able to isolate and remove very specific noises that were nearby, especially in these urban areas. That's more important than ever. So I think that you all may have seen some things on ambient noise interferometry or passive interferometry previously. And you may know that you need to actually pull out certain kinds of signals. So here we were actually able to develop some machine learning tools to just isolate and remove cars that we knew would cause issues in our interferometry. And this also, when we were trying to evaluate whether our signals that we were trying to pull out that estimate sort of our wave equation Green's function, when we needed to evaluate if they were actually getting any better, we needed to do all of our quality checks across the whole array so that we could really know whether things were getting better. So having these very dense arrays in urban areas is something that would be almost impossible to maintain for more than a few weeks, maybe a couple of months. But we were able to maintain this for several years at relatively low labor because of the DAS technologies. We could also use this for detecting earthquakes. So here are some small nearby events that Siwan Yuan and I had analyzed. So this was less than a magnitude 1. This was a magnitude 0.8, about 5 kilometers from the array. And we could see a little bit of that signal throughout the array. But then as we started to calculate average features, things like what's our envelope, what's our spectrum average across many channels, we actually got a lot more powerful ability to be able to detect different signals and different earthquakes that were happening. And it wasn't just these nearby small events, but we can also see things like teleseismic events. We can get very low frequency signals. You see that this is over just a couple of minutes here, but you can see some very low frequencies there. And these are including signals that are in that 0.2 up to about half a hertz range. So getting back to that question about the broadband response, this one over here on the left is more like 8 to 12 hertz where we're getting a frequency response. So it depends on what our source of energy is, what we're actually going to pick up, but the sensor itself, very broadband.
I think we have some questions in the chat. So the first question is there an instrument response in the DAS like in a broadband seismometer? Maybe this ties into the previous question, maybe.
Oh yeah, there is. I'm going to get into some pictures of how you start to calculate what that instrument response is, because it actually depends on, it's not just a single point has an instrument response. There's a whole adjustment on what's your incoming angle of your source, what's your type of source and like wave motion, what's your actual like gauge length setting on your sensor. And so there's actually a lot of factors that go into calculating that instrument response. And there's not a standard way of reporting what that instrument response is. So that's something that a lot of us in the community are pushing for. And there are some efforts, especially led by Iris and others, to standardize that kind of instrument response so that it's very easy to take it out. But as it stands right now, we all have to do these corrections for ourselves. I see there's one other question, maybe.
Yeah, so the question is, in my limited exposure to DAS, I often hear of coupling being brought up, i.e. potential limitations in sensitivity based on a lack of coupling between the fiber optic cables and the ground. So the questioner is wondering if you have some general comments or insights on coupling issues when using DAS. Is it just a case of ensuring proper installment, or is there something else?
Yeah. So I think that the biggest thing is installation technique. With these kind of, like here, I'm showing some data that was collected by just fiber that was run underground, not glued into place. It's just relying on gravity and friction with the conduit that it's sitting in. It's not buried and closely coupled to the soil or anything. So in this case, I was really shocked that we were able to detect something this small. I think that it depends on the application how important that is. So when it comes to things like if you're trying to do VSP imaging, for instance, where you have your fiber hanging in a well, there it's really important to make sure you've got your fiber sort of coupled tightly to the side through either clamps or like cementing in the well is the best way, so that that fiber isn't wiggling around and giving you spurious oscillations. But when it's just a horizontal fiber, and if you otherwise wouldn't be able to have any data there, then having this kind of data that may have a lack of a little bit less sensitivity can still be good enough. And if you are able to do calibrations based on known event magnitudes, based on standard sensors that are nearby, then sometimes that can be good enough for your purposes. It really depends on your application though.
I think that ties really well into the next question, or perhaps answers it. And the next question asks about what the state of the art is in terms of assessing the coupling, in particular for dark fibers, and also what is the proposed technique to bury temporary installations to ensure proper coupling.
Yeah, so I think that if you are able to actually bury your fiber and have the soil kind of collapse in on the, or just directly bury where you're backfilling a trench, let's say, that's almost always going to be better than just a dark fiber installation. But it may be overkill, and it may be not, and it's almost certainly not affordable for a lot of our experiments. So I would say that sort of the state of the art right now of what a lot of people do tends to be more of looking at those kind of known events, trying to match what are those amplitudes of standard seismometers with our cable, our dark fiber. There is some ongoing work by Zhang and Zhan and others at Caltech that I think really is kind of hitting at this problem of trying to get more reliable understanding of the amplitudes that ties in some of that coupling condition. I know there's other people in the past have tried to do some characterization of this in the lab. So there's a paper by PAP, P-A-P-P, that kind of hits on some of that quantitative coupling analysis. And over at the Sacramento fiber optic array that was run by Lawrence Berkeley Lab, Nate Lindsay had done some characterization of that in the field with a dark fiber array as well. So I'd encourage you to take a look at that experiment.
I think we have one more question about coupling. So the question is, if one has no real assessment of the coupling along the fiber, it is not possible to use the amplitude information of the strain, either absolute or relative. And so the question is it stable, comparable of time, or is it actually inelastically strained over time due to the significant deformations?
So I think that what's being asked is like, do you have your cable displaced permanently by anything? And so if you had, let's say like a really large earthquake nearby and you thought that your fiber might have been enough to really displace your fiber, then you're not going to want to look at those kind of time-lapse changes necessarily at that very sort of low frequency. But and you also might want to reevaluate whether your geometry is still accurate. So that would take a really large event though. With typical small earthquakes, I don't think it's enough to really displace the fiber that much. I think that, the comment about can you use relative amplitudes? So again, it matters whether one of your events has been large enough to displace the fiber, but if that hasn't been large enough to displace the fiber, then you should be okay comparing your amplitudes from one event to the next, at least in a relative sense of how big those were. You can also, if you know that you have the same coupling conditions, even if you don't know exact characterization of your friction coefficient, but you know that they're, let's say, the same kind of conduit that it's installed in, or the same kind of trenching and the same kind of soil qualities, that's probably good enough to at least say relative amplitudes between neighboring, nearby channels. So, yeah.
And we have one more. Do you have any events, for which you've compared a broadband seismometer and DAS to see differences between them?
Yeah. So I would encourage you to take a look at these two references here that I was co-author on. And there are some of those specific comparisons there. This one was this one is just one of the events. So that will give you a little bit of comparison. So, yeah.
Yeah, maybe one last one related to the previous question. And maybe I would say that after this, we can maybe relegate this conversation to the Slack so that we can move on with the presentation.
Sounds good.
So let's say that one part of the fiber is somehow better coupled to the ground than another. And then one would see a difference in amplitude, which would not be related to the actual damping or the wave field amplitude.
So it would be related to the wave field amplitude, the coupling, and the damping, all of that together. But if we assume that the coupling is static from one event to another event, then it only comes down to basically those last two factors, once those are all kind of multiplied out. So I think it would, at least from one event to the next, it would tell you something about the relative change in that wave field amplitude. It wouldn't tell you exactly what the wave field amplitude is of either of the events, just relatively how they compare. So, yeah.
Thanks.
All right. So I guess also getting back to one of those questions. So here's at least, these aren't broadband seismometers, but they're node data. So we did do a comparison during some controlled Betsy gunshot experiments, where here are three components of inline, crossline, and vertical data. So inline is sort of typically what we think of as sort of the most comparable to DAS. Although in our DAS data during a Betsy gunshot, we actually saw some of the same events as vertical nodes. And so this told us we were also getting some of those Rayleigh wave events that are kind of rolling forwards and down. And so we do have some of those kinds of comparisons as well, where we're able to see at least some of the same events for active seismic data. One thing that we usually don't see a lot of in DAS data is if we have any kind of air wave that's moving over the surface, our DAS is typically buried, and so we won't see a lot of that. So it can be a little bit cleaner for some of those things. It's certainly easier to pick out those events also when you have much higher density than in your sensors than you would have with traditional nodes. One of the other applications we've used this for is for permafrost thaw monitoring. So you tend to get seismic wave field velocity drops when permafrost thaws. And so there's a series of experiments that I got to help with data analysis on up in Alaska, led by Jonathan Aho Franklin and Anna Wagner. And we're doing another experiment over the next couple of years with Penn State up in Utqiagvik, Alaska, looking at some of these similar issues where we're trying to pinpoint what are these locations where we're actually getting drops in our surface wave velocities or our S wave velocities. And being able to have sort of this very fine sampling that's available through DAS that's maybe 1 or 2 meters spacing, that actually helps us a lot, given that the spatial scales over which permafrost tends to thaw actually oftentimes has very small scale changes in it that matches roughly that few meters to maybe 10-meter kind of scale. So here are a few of the experiments where this was done. And I'm going to come back to some of these examples as we get into looking at that instrument response. Another example of what we're using this for is for monitoring seismicity on glaciers. So here's the Rona Glacier experiment that was led by Fabian Walter and Andreas Fichtner last year. I'm helping out with some of the data analysis. And here's an example of what just a few hundred channels of that data looks like. And really, this is actually more than 10,000 meters worth of channels. And it's about 4 meters per channel. So a couple thousand of these channels, and there's a lot of details in there. One of the students that I'm co-advising, Julius Grimm, has put together some event detection in here, and we get a lot of noise in these glacier environments. So it's especially important that if we're able to use a whole array to detect any seismic events that are happening, which we call ice quakes, that we're able to actually ignore the other parts of the array that might be very noisy during that time. So having the array over a large distance with fine scale and really broadband sensitivity is super helpful in these kinds of applications. So there's a few of the ice quake type events that we're looking into. So just bigger picture, fiber optic sensing is really enabling us to have dense sensor spacing, long distances. We're going into new locations where it wouldn't have been possible to have a dense seismic array previously. We've got broadband response. We're able to record our data for much longer than we ever could before, simply because it's low maintenance and it's a low labor type of acquisition once you've got it installed. So, okay, now let's get into the interesting stuff. That's like, what does DAS really measure? I know there were some questions earlier about what is this sort of, is there kind of an equivalent to the instrument response that you get for a broadband seismometer? So the quantity that we're recording is typically something like axial strain rate. There are some instruments that will report something that's actually an axial strain along the direction of your fiber. There are some instruments that will report something that's called a velocity that you oftentimes will just process into a strain or a strain rate. But let's just look at this one version that's sort of the most common. So let's say I've got my fiber optic and I've got a little section of it that's my gauge length, G here, and I might have some tension and compression in different parts of my fiber. So if my fiber is under tension, it's going to get a little bit wider. And then if it's under compression, it's going to get a little narrower, right? And so what we're measuring here is actually what's called a strain rate. And so we're used to working with maybe velocities, accelerations, and displacements more often in seismology. So if we had to put this axial strain rate in terms of a velocity, and I said that my velocity was u, and I'm just going to assume that I've just got a 1D kind of signal in the x direction, then I would just take my spatial derivative with respect to x of u sub x here. So that's just going to be a spatial derivative in the x direction. Now, we'll get into what this means as a tensor in a little bit, but that's just our simple 1D case. So from just that basic understanding, we can start to predict what our DAS should actually be reporting and what should be some characteristics of our DAS array data. So we already know that if we're measuring, let's say, a velocity versus an acceleration, well, that acceleration is like a time derivative of our velocity. And based on just our standard properties of the Fourier transform, we know that that's the same as basically multiplying our Fourier transform of our velocity data by I times whatever our frequency is. So it basically is going to boost up those high frequency values in our Fourier domain if we were to look at our spectrum. And as kind of an analogy to that, then we can look at this scenario where we're looking at the spatial derivative of our data. Instead of looking at velocities, we're looking at strain rates. So we take a spatial derivative and then take our Fourier transform in x if we were to be, let's say, like calculating an FK transform, something like that. Then we're going to get something that's like minus IK times our Fourier transform. So we're going to be boosting our high wave numbers. That means that when we look at our data in space versus time, and then if we look at it in the FK domain, all of our FK domain, if we were to be doing like a time derivative, we would be boosting up what's in this top part. If we're doing a spatial derivative, that's going to be boosting everything out at these edges. That's these high wave number parts. And in space, what that's going to look like is if we were to cut across a particular time sample across all of our channels, it would look like a much ringier waveform that we would be looking at there. So it's sort of spatially ringier than what we would record with an array that records velocities.
We have some questions in the chat. So,
okay, one of those I'm going to get to at the very end about the data quantities. So I've got a little bit on that. And I'm about to get into some of the stuff on the components and like the directions. So great. Okay, so we know that we're going to average our axial strain rate over a gauge length. And so if I were to say, what's the data that I'm recording? I'm going to take that velocity in the x direction just for my 1D problem to start simple. So I take my velocity in the x direction, take its derivative, and then I'm going to integrate from my start to my end point of my gauge length that I'm going to measure over. And if I'm integrating something that's a derivative, well, that means that I can basically use my calculus rules to look at what's the difference at the two endpoints of that thing that I was taking the derivative of. And so what that means is that I'm basically taking the difference of two velocity measurements in the same direction as my fiber optic cable. So that's basically taking the difference of two traditional geophones that are horizontal, or two broadband seismometers, whatever velocity sensor you're working with, that are in the same direction as the fiber, taking their difference. And so that's just another way to think about each of these dash channels and what it's recording. But of course, this is just the 1D problem to start with. And we're not the first people to think about using strain sensors. So even as early as the 1930s, people were working with strain sensors. They weren't based on fiber optic technology. Lasers didn't even exist at that point, but just traditional strain sensors. And for different types of waves, longitudinal waves or transverse waves, Benioff actually looked at different incoming angles of our waves that were coming in, just simple plane waves, and said, okay, what's going to be our amplitude response to each of these? And so let's say that I were to have my strain sensor just oriented horizontally here. Then coming in from the right or from the left, if I had a longitudinal wave, like let's say a Rayleigh wave's horizontal component or just a P wave that's coming across, then I'm going to be really sensitive to things that are in line with that strain sensor, right? Coming from either the right or the left. But as I go around to other angles, I'm going to get less and less sensitive. And that's also true with geophones. But with a strain sensor, it's actually got a much quicker die-off to the sensitivity to those other directions. So anything coming from up here on top or the bottom, it's much less sensitive to than the geophones or any velocity sensor. And with transverse waves, we actually get a very different kind of behavior. So if you have a shear motion, an S wave, or a love wave, you're actually going to get totally different behavior. So the geophone sensitivity to transverse waves, that would be a geophone that's horizontal, oriented in the same direction, it's going to be very sensitive to shear motions from up here and down here. But actually, with a strain sensor, you're going to get basically 4 loads of sensitivity that are actually emphasizing sources coming from these kind of 45-degree angles, which is totally different than what we had with our strain sensors. So this can actually cause a really different response to signals coming in from different angles. So where does this come from? What's actually going on behind the scenes? So our strain rate is actually a tensor quantity. So if we had our whole strain tensor, it's basically, okay, only these top 6 sort of components matter here. There's 9 total, but it's a symmetric matrix. And so we're going to be looking at all of our different derivatives of each one of our directions of our particle velocities and taking the derivatives in all 3 of our directions. And so we have this whole tensor that reflects what's our whole strain rate. And if we just had a 1D problem where we just had waves kind of traveling left and right and in our x direction and our fiber also oriented in that direction, all we would have to care about is that entry. But oftentimes we have our fibers in different directions relative to our sources. And so that's kind of what's going on in that Benioff paper here, where we're looking at different source directions and looking at what is the sensitivity there. So to actually look at those different directions, we have to do what's called a tensor rotation. And that means we apply a rotation matrix to either side of our whole strain tensor. And we're not actually observing this whole strain tensor. In fact, we're just observing the parts that's just the very top left corner of the result of this. So it's just taking these terms, multiplying them by this matrix, and these terms here. And so this leaves us with just a single scalar measurement. So I think for this question about if DAS has components like a seismometer, if you create an array that has channels pointed in different directions, you can kind of recreate different directions. But these are still just components of this strain tensor. So you need to be careful to think about how are you rotating those. It needs to be done with these rotation matrices on either sides instead of just a single rotation matrix like you would for a velocity measurement or an acceleration measurement. So if we just worried about, let's say, longitudinal waves, we're only going to worry about this first term. It's this cosine squared of the angle between our source direction and our actual sensor. And so sometimes you'll hear that quoted as like a sensitivity for DAS, and that's for longitudinal waves. But if we've got a shear motion, we worry a lot about these kind of cross terms in our derivatives. That's what's really the motion that we're detecting in those shear waves. And so there we've got cosine theta times sine of theta. And if you look at a polar plot of that, that's going to give you those 4 lobes like we saw in the earlier slide. Of course, it gets a little more complicated with our DAS systems where we've got to think about integrating over a gauge length, but it's not too different as long as we're looking at just long enough wavelengths. So let's say if I were to look at Rayleigh waves and Love waves, our particle velocity measurement, again, has just sort of 2 lobes in response to plane waves coming in. But our Love wave response also has 2 lobes. But then if we were to look at our actual point-wise axial strain rate measurements, which is kind of an idealized DAS, we've got 2 lobes for our Rayleigh waves and 4 lobes for our Love waves as our sensitivity. And of course, then when we look at having a gauge length in there, let's say that if my wavelength is twice my gauge length, I've still got 2 lobes sensitivity for Rayleigh waves. It's pretty similar, and 4 lobes for my Love waves, but they're a little bit misshapen. Things start to get a little wonky there. So we want to be careful about actually accounting for that gauge length sometimes. As our wavelengths of our waves start to get smaller, that is to say, if we look at higher frequency waves, we start to get these sensitivity lobes kind of even more misshapen. So if we have a wavelength of 1.2 times, it's very unusual looking. And 0.9 times the gauge length as our wavelength, suddenly we've got 6 lobes of sensitivity for our Rayleigh waves and multiple lobes for our Love waves. So it really gets to be important for high frequency data that we actually account for all of this math of what's going on with our sensitivity of our DAS. So unfortunately, there's not a standard instrument response that comes with the data, so you have to kind of go through this math to figure out what you should expect for different frequencies. And there are different ways to kind of visualize what is that angle of your incoming plane wave and what's your wave number and how sensitive you expect to be. And this is really observed in our real data. So here's an experiment from, I think, a VSP walkaway study using P waves where they plotted what is the amplitude response to different waves versus cosine squared of theta. So just getting that sort of simplest sensitivity response for longitudinal waves or P waves. And we really see a good match in our field data. Okay, so we know that DAS gets us the correct arrival times, but when we switch from particle velocity to an axial strain rate, we really get different sensitivities there. And as we get to smaller and smaller wavelengths on our data or higher frequencies, we have to really pay attention to this sensitivity. So our phases are also recorded a little bit differently. And so let's say that we record an earthquake. Here's the Stanford array down here, recording an earthquake up in Berkeley that was a magnitude 3.5, so pretty big. Here's our P wave arrival and then our S wave arrival. And we're just looking at it throughout our whole array. And one thing we can start to do as we zoom in on the data is looking at different corners of the array. And we start to see things where we oftentimes get opposite polarity. So here I've highlighted a region that's just right at the corner of the array. And we tend to get these polarity flips here. And in fact, that's actually just an effect of doing this sort of tensor rotation of our strain tensor. So if we are observing our source at something that's been rotated by 90 degrees, and we're during an S wave, so we're looking at that shear motion and really emphasizing this term of our wave field, we're going to get cosine theta times sine theta. And if theta gets 90 degrees added to it, one of these is going to get a negative sign added to it, and the other one isn't on these cosine and sines. And so it's just basic trigonometry rules suddenly that give us that we're always going to get these phase shifts at corners. Okay, so I think that we're pretty low on time. Actually, I'll just provide some of the slides for the GitHub repository for this section, but this is all about sensitivity of DAS signals when you're doing ambient noise interferometry. It's maybe a little bit more specialized, but I will say that ambient noise interferometry is awesome. I love it. This is an example of doing it with a node array throughout Long Beach, California. And it lets us do seismology at relatively low cost for our experiments. And when paired with DAS, it's a really powerful tool because we can leave out our sensors for a long time. So if I were to do just a simple experiment of setting off a bunch of sources around a couple of geophones first, and record all of what I would get as a velocity in this sort of horizontal direction, I can see there's different areas where I respond more strongly or weakly. And when I calculate my cross correlations, I get similar patterns. And I can get something that's very close to a wave equations Green's function out of that. And so that's just with geophones, right? But when we actually tested this out in practice with DAS data at the Richmond Field Station, and here's an example of that data, so it just looks like a total mess. We can actually get really coherent signals from just like 10 minutes of recording to start with. And so this actually ended up matching our geology quite well. And we wanted to know why. Why does this work? So if we actually repeat that same sort of synthetic experiment with fiber instead of geophones, I've marked the fiber data here in red. We see that we actually get similar patterns in our cross correlations there. The timing is all the same, just the waveforms look a little different. And after we average over our many different sources that we've recorded, we get pretty much the same Green's function estimate there that was correct. But when we have love waves, things are very different. So our cross correlations suddenly have areas that they're responding to very strongly that are at these 45-degree angles, like I mentioned. Or if you're looking at higher frequencies, they may be at different angles. So suddenly our cross correlations that we're going to average over a bunch of sources, we've got like 4 lobes of strong responses. Whereas with the geophones, we just had 2 lobes. And so when we average these, we see that the red signal, which was our average over the cross correlations for our fiber, suddenly give us kind of junk in the middle. So with love waves, it's much harder to do ambient noise interferometry if you just have sensors right across from each other. So if we add in Rayleigh wave signals in this experiment on top of our love wave signals, it actually gets even worse with this kind of an orientation that for someone who does ambient noise interferometry with nodes would be very natural for extracting love waves. In fact, this is like a worst case scenario with DAS data. So just to look at why we care about this, well, we can actually look at other parts of our array. So let's say I've got 2 fiber optic lines that are parallel to each other. I don't actually want to use the fibers that are the channels that are right across from each other. Instead, I want to look at ones that are a little bit offset. So I'm going to have a virtual source over here, cross-correlated against all my other sensors on this other line. And if we were to simulate what should we be recording as our ambient noise interferometry results that should approximate a Green's function, we see that these sensors that are close to being right across are actually kind of junk. But as we move farther away at larger offsets, these channels down here are giving us signals where we can actually pick out Rayleigh and love waves and those arrivals. So they can actually give us usable signals. So we want to throw those out. And if we have different orientations, like let's say in our urban DAS experiments, we're oftentimes working with sort of a zigzag array. Even in some of our environmental experiments, we sometimes get kind of offsets at different angles. And with those kind of setups, we actually get even cleaner signals that we can extract. And so it is possible to get different wave modes out of our DAS data that's passive, but we have to be very careful about understanding that kind of angular response of our strain and strain rate data before we can start to really interpret these. So this is very much what led us to actually understand what we were getting out of the Stanford DAS array when we were looking at various signals that showed up throughout that array. So being able to understand which ones are reliable and which ones weren't. And in Fairbanks, Alaska, at the permafrost thaw test that was up there, did some analysis along with Nate Lindsay, and he really dug into some of these details of how does this match up with the real field data. And we actually see these kind of strong and weak patterns that we predict from our synthetics here. So it really does match our field data. Okay, so the last question I think that was up on the Q&A, it was about volumes of data. So just to give you a feel for what data volumes a lot of people use, we're typically getting somewhere between like 10 to the 5th and 10 to the 8th data points per second. That's like floating point values. So we say how many points per channel per second, and how many channels are we recording on, which is oftentimes thousands of channels. And then here I've plotted just when were these experiments happening. So we have some that are very low rates, some that are much higher rates. And when we look at our cumulative amount of data over here on the right, we actually see that just like 9 experiments have actually added up to something like 800 terabytes. And that wasn't even choosing the largest 9 experiments. It's just the ones that are circled in black here. So a mix of low rate and high rate experiments to kind of give a feel for what are the data quantities ranges. And comparing that amount to all of the IRIS Data Management Center archives, it's actually about the same amount of data, except that it was only collected by a small collection of seismologists over like a 5-year period. So if I were to squish the time axes to be more reasonable or more comparable between these two plots, you actually see a really fast rate of data being acquired in DAS. And this isn't even including the highest sample rate experiments. So of course, this means a lot of hard drives, and a lot of groups are just kind of locally storing their data on their own HPC systems or computer clusters at their universities. There's some efforts right now that are going on for community data archives. And so I'm really hoping that that grows a lot, because it actually has led to a situation where not everybody can get access to the DAS data. Or if you do get access to it, you have to be really clever about how you use it to manage those data quantities. And so a lot of my work is really on how do we reduce our data quantities while still maintaining what's meaningful? How do we advance our algorithms to work on those reduced data? And how do we work with our data if they have to be up on public clouds? Many of the archives are starting to look at cloud solutions. So for instance, the Department of Energy's Open Energy Initiative for DAS data and other data that's tied to geothermal energy, that's all hosted by Amazon's S3 services now. Much of the rest of the data that's out there that's public for DAS is on university archives, sometimes GitHubs pointing to Google Drives, sometimes even old-fashioned mailing of hard drives. And here's a quick summary of some of the data sets that are out there. Since this will be up on YouTube, I hope you can pause the video here and kind of take a look at what's there. But there are several of these data sets that are open, and I know that there are many more planned to be released in the coming few years. And so I hope you'll take a look at some of those as well. So now we've got some time for I guess, more Q&A, or we can do our Jupyter notebook and exercises. Let me just show acknowledgements real fast to make sure I show all my collaborators and funding sources and everything that supported some of the results that were on here. But yeah, good.
Yeah, I was thinking we can maybe we typically take like a 10-minute pause or so and give people a chance to get some water, but maybe then we'll move on to the lab session.
Sounds good.
Thanks so much.
Yeah. I'll try to answer some questions in the chat also if there are any there.
Yeah, right now it looks like, yeah, I think you've covered all the questions so far. I think, yeah, there was a one question about whether it has northwest, east, north, south, east, west, or vertical components like seismometer. And I think you also answered that, and so I think that's everything.
Great, great. All right, I'll be back in 5 minutes or so. So good.
Yeah, I think we can probably begin with a lab session.
Sounds good. Here, I'll pull up my screen here. And I guess I'll just do kind of a run through of what's here in the notebook and show you which parts you can kind of modify and edit as you get started on some of the exercises. And then also point out there's a bunch of useful links in here that I hope you all will check out. Good. So I guess you've already downloaded the notebook from the GitHub repository. And hopefully you all saw the links on the Slack about downloading the data. So right now I've got Jupyter Lab running just on my laptop, and in the same directory as my working directory, I've already downloaded my files that have my data. So I've got this CSV file down here that's going to have the coordinates of all of the channels in my data. Now that's something that I actually used to need when I worked with the data before it was put into a nicer format. Now it's actually not necessary, but at least it's something small that if you're just getting started and you have a slow internet connection, you can at least start to check out what the geometry is and start to do some theoretical predictions of what your sensitivity should be to different wave sources and different directions of waves. And then I've got these two other files, which are HDF5 formatted. Now, regardless of the data format that's used, whether it's HDF5 or SegY, ProDML, ASDF, whatever it is, most people that are recording DAS data continuously are doing some kind of naming convention where they'll typically have like either 4 or 2 digits for the year, 2-digit day, 2-digit month, 2-digit day, and then some indicators of what's the hour. So like 2 digits for the hour, the minutes, and then the seconds for the beginning of the file. So this one, it has 21 at the end, and then the next file has 51 at the end. So this file basically started recording 30 seconds before the next file. And there's actually a ton of these files up on the DOE's geothermal data repository. And so you can go and download any of the files from this, but just to give you a feel for what you're looking at when you're getting into a DAS data, that's kind of the typical naming convention. Sometimes there's some indicators, what's the milliseconds of the start time or some things like that as well. Okay, that's what we've got in this folder. And so the goal with this is just to get familiar with an open DAS data set. This is the Brady Hot Springs data that was one of the first data sets of DAS that was actually made totally public to anyone. So it was collected by the Porotomo team. Kurt Feigl is the contact for this open data set over at University of Wisconsin. And it's posted on DOE's geothermal data repository. So if I click on this link, you can actually go and explore all kinds of data that was recorded at this geothermal site. There's not just DAS data, there's node data, there's all kinds of information about how did they actually map their locations of their fibers to the actual channel numbers. That's the tap test data, for instance. There's data that's, when it says DAS V, this is DAS data that's actually down a well, vertical. And then we're going to look at some of this DAS H, that's the horizontal DAS, just on the surface, trenched into the ground. So I just wanted to point you all to this resource as a place where you can explore for more data sets that may be complementary depending on your interests in seismology and geophysics. So you can find some more information up here about it. And here's a bunch of references of what people have done with this data already. I think that one reference that's going to be really helpful to read through after you go through this notebook is checking out this paper right here. It's in GJI. It's focused on a particular earthquake that happened, magnitude 4.3 at this location with this DAS data. And so you can go and actually start to analyze, am I seeing the same thing in the data that they saw in their paper? And can I recreate some of those types of analyses there? So I'll just point that one out to you. Whoops. Well, there we go. All right, so to actually work with DAS data, very few people are actually using the typical kind of mini seed or SAC formats that people will use with single station seismometers. More often, we're thinking about our data as being in an array of channel versus time, and we store it all into matrices. And typically we'll kind of block it up in maybe 30-second, 1 minute, 5-minute kind of chunks. we just store that one big array. So in this case, we're working with data that's stored in an HDF5 file. Sometimes people will use SegWi or other things. And in fact, if you go up to one of the links up here, here's the original notebook that this was kind of based on that I had made. I've actually got a different version of this that works with SegWi formats of data from this same experiment. So just to let you know, we're mostly focused on doing array processing with our DAS data. So we don't actually need to work with OBSPy very much. It's not very natural to work with those individual traces. Here and there, I'll oftentimes use OBSPy for just small amounts of processing because it has a ton of useful functionality. But when it comes to working with that larger scale data, it's oftentimes better to work with things like SciPy's signal processing toolkit or those kinds of things, more array operations that have been really optimized for working on matrices. So the packages that we're going to work with are going to be NumPy, Matplotlib for plotting, SciPy's FFT pack for Fourier transforms, H5Py for reading those HDF5 files, and CSVs for reading our array geometry file if we just want to work with that. So I've got some commands down here that will let you actually download the data. I haven't tested out this Windows one. I'm sorry, I only have Mac and Linux, but hopefully someone who uses Windows can test that out, and I'll correct it if there's any mistake there. Or you can just navigate to these links up here and just download the data from there. You just have to choose the appropriate file names. Okay, so I've already downloaded these. I'm not going to do it again because it takes a few minutes since my internet is a little bit slow. But I've already got those files there. And first, let's take a look at just what is the array geometry like. So I've got this, if I look over here, I've got this surface DAS, DTS, UTM coordinates. And so this is basically a CSV file where the team just put down, here's all of our locations, UTM coordinates east, west, and north, south of where our channels are. And this is oftentimes something that is not automatically embedded in the sensors because we don't do the acquisition of a single sensor where we might just already have that metadata of the location tied to the sensor. Instead, we have to go through our data after we've recorded it, and we have to have done certain experiments, which we call tap tests, to actually assign those channels in our data to a location in space. So in this CSV file, we actually have some junk channels at the beginning. It's not uncommon in DAS data to have some junk channels either at the beginning or the end. And sometimes that's just because of a software interface thing in the interrogators, depending on what interrogator you're using to collect the data. And sometimes there's actually channels that are maybe in a building or something like that where you just don't care about those. So you're not going to read their locations anyways. So I'm just going to read this file using a CSV reader and fill in my channels, my X locations and Y locations here. And then I can just do a little scatter plot so we can get a feel for this array. So this array is spanning more than 1 kilometer wide and more than 1 kilometer high. It's about 1.5 kilometers high here. And so you can see that we start down here and our fiber just winds along this really zigzaggedy path here and then goes back down and goes back up. So you can already start to imagine just by looking at this geometry that, let's say if I had a wave source down here in the southwestern corner of the array, I'm going to start to pick it up on one part of my data, and then a totally disjoint part of my data is going to pick it up at the same time. And then later on, I'm going to actually get the arrival to pick up on another area. So if I were to plot out my data in like a matrix, it would have kind of a zigzag characteristic to it to sort of match this geometry actually. So my arrival times are really influenced by what this geometry is like. In this experiment, there's actually a road on one side. And so it's good to know about those kinds of things as well. So reading all of those references that are up at the top of this notebook can help you kind of know where noise sources may be coming from. Okay. So one thing that we oftentimes want to do with these kinds of arrays that have a lot of zigzags, or let's say an urban array where maybe we're traveling, we have fiber optics underground and they're kind of following streets. So they tend to have a lot of that zigzag, is maybe we want to just pick out some straight segments to focus on. So I've provided some code here so that you can just start to look at what's the difference between neighboring channel locations so that you can estimate what their directions are and look at what their normalized inner products are of successive channels to see which channels are actually going to be like close to parallel with each other. If you have a channel that's sort of at a corner, then when you look at the inner product that's normalized with the previous one, well, you're going to have a cosine that's going to be close to the cosine of, let's say, like 90 degrees. So close to 0. It's going to be a small value. Okay. And that's what we see is most of the time we're just going along these straight segments, but every once in a while you get to a corner and that normalized cosine drops down. So this gives us a nice, easy way to kind of threshold our data or our channel setup. And we can start to pick out where are our corners just based on what this map is. Depending on your data format, because this is not a, DAS data does not have really good solid standards across the community, it's pretty common to just get a list of locations. And so you can reuse this kind of code anytime you get a list of locations if you're trying to look for where you have corners or turns, where the data may be harder to interpret, and you want to just be able to pick out little straighter segments that are easier to work with. So here I've just done a little scatter plot of what are all the picked out locations. You might wonder like, what's the influence of that threshold? So check out like this top left corner here when we've got a threshold of 0.8. If I change that to 0.7, suddenly I'm less sensitive to a very slight bend in my fiber. And so if, it depends on your application, on how willing you are to deal with slight bends in the fiber, but hopefully that gives you an idea of what's going on there. Okay, so that's just working with our channels. And you probably want to know, how do I actually read the data? That's my strain rate data at every sensor location at every point in time. So first, let's just read one of these 30-second files. So I'm just going to choose this first file out of the two that I've got, the one that ends in 21. And I'm just going to create an HDF5 file object here in read mode. And I'm going to print out what are the keys, just so I can start to explore it. Again, we don't have a lot of community data standards in DAS yet. And so a lot of times you're given some HDF5 file and you just have to explore what are the keys available to you. Okay, so I've got something with channels, something with CRS. Maybe we don't know what that is, or just DAS. Isn't everything DAS in this data? Here's something, T is probably something to do with time, right? And then we've got something labeled as trace, and then X, Y, and Z. So let's start looking at what are these. Okay, channel, X, Y, and Z, that's pretty self-explanatory. It seems like someone collected the data and then they actually started to attach locations to it maybe. So let's just read each of those arrays or those objects and find out if they're arrays. And then we'll start to plot those out. Okay, so we can check like what's our number of channels. And so we've got 8,721 channels at this location. You can imagine that that's something that's easy to do with DAS, where you just have maybe 1 meter spacing, but really hard to do if you had to lay out 8,000 seismometers. It would be extremely time intensive. So it just gets at what is the scale of these systems. All right, so then we can start to look at what is our location. And again, we've got those same locations as before. This is just that someone has taken that CSV file and they've attached it to the data itself in the HDF5 format. So this data actually used to only be available in SegY format, which you can look up that other notebook on how to work with. And the SegY data, we didn't actually see all of these locations tied to our data always. And so this was really helpful to have all of this together in just one file. And so a lot of people in the community are using this HDF5 format because it's great for storing different multidimensional data arrays as well as metadata alongside the data. So with DAS, since we don't have those kind of standards, it's really good to have easy ways to explain what your metadata are with those kind of keys. Okay. So we can also check out, like here I've got Z versus what my channel index is. And so we can see like what's our elevation of each channel. And you can see the different zigzags kind of going up slope and down slope as you go through the array here. Okay. One thing to note if you're working with these HDF5 files is that the arrays that you read are not actually NumPy arrays strictly. So you have to do a little bit of slicing the arrays up to get them to act like NumPy arrays. So depending on your system and how your environment is set up, you may have to add in this little square bracket with the colon sort of force a slicing of these HDF5 objects so that they'll act like NumPy arrays. So just a quick note as you're starting to do some analysis with these data that you may have to worry about forcing them to act like NumPy arrays.
I think we have a quick question in the Q&A about whether we can use DAS for earthquake early warning.
Oh, that's a great question. Actually, so like, I think it should be possible. What the biggest question is really whether it's going to be approved as part of earthquake early warning systems, because that's always a big part of it. Is early warning has this big policy side to it, but when it comes to being able to spread over large distances, get close to any potential earthquake sources, I think that those results I showed in the talk from that Siwan Yuan and I had worked on, where we could see both our P and our S waves on like a quite small earthquake, just a magnitude 0.8 in a really noisy area, like that was really convincing for me that like this has potential, but it's still something that's under investigation. So I wouldn't say that it's something that's been approved. I wouldn't say it's something that's been proven, but it's certainly something that's on the table as you know, something as a potential area that is definitely worth investigating more. Yeah. Good. All right, so let's take a look at how do we actually get our DAS data itself. So let's just check out some of the other keys. So one of the next ones I checked was, what is just DAS? So, okay, we can get that data and then we can check its shape, and it's got 30,000 samples by 8,721. So to me, I know that with DAS data, we're typically doing hundreds or thousands of samples per second. I know that this is 30 seconds of data, and 30,000 samples, well, this is my 30 seconds of data at 1,000 samples per second. Now, of course, we could actually dig in more on the metadata and all of the settings to verify that, but basically this is our actual array of strain rates at every time sample and every location along the array. All right. And I see one of the questions in the chat is asking about init geometry. So just going back up here, was that zigzag profile done on purpose for better sensitivity to waves arriving from multiple directions, perhaps, or was it just a limitation on where the cable could be installed? So if I remember right, I think that there might be one obstacle at this site, but from what the people who acquired this from University of Wisconsin told me, as far as I know, it was more about being able to test out what was that sensitivity to different orientations. So different source directions and all of that, making sure that there was always some fiber in line with those different sources. So yeah, I think it would be a lot easier if it weren't that zigzag path to process the data and to interpret it, but also it means that it's a really great test for a really great data set to test out any questions you might have about sensitivity to different orientations. All right, so along with our DAS data, we actually have to find, you know, timings for each one of our samples, right? So we've got locations along one axis and then times. And so here's how we just read what's our number of seconds per file and how many samples do we have per second. So all of our channels are exactly in sync with each other. So maybe if you've worked with individual seismometer data before, each one of those sensors, even if they're all set to the same sample rate, they're not necessarily synced up to be sampling at exactly the same time. But with DAS, all of those channels that we're recording data at are synced up to be recording it at least close enough to the same time, up to the speed of light. And a seismic wave doesn't come anywhere near close to the speed of light. So we're going to say that all of our samples collected on our fiber optics, at least in this kind of kilometers to tens of kilometers scale, are going to be collected at exactly the same time. So this array here just has our 30,000 samples that tell us what time each sample is taken at. And we could just plot an individual trace. We could pull out any channel of interest, slice up our data array that's a matrix, just grab one of its columns, and then just plot what that looks like. And this is actually during the arrival of an earthquake. And so we see that earthquake show up here. And of course, it's going off into the next file. So as one of your exercises, you're going to have to figure out how to kind of piece together these files to make sure that you're able to work with sort of multiple arrays stuck together. This is something that It happens all the time in our DAS data processing. So we can see that earthquake coming in just on a single channel. And of course, our DAS channels have relatively low signal to noise ratio compared to, say, an individual broadband seismometer or long period seismometer, but we've got a ton of them. So we want to also be able to visualize all of these channels, because what if this is just kind of a messy looking channel? Maybe it's noisy nearby, something like that. So if we try to do that with just a bunch of wiggle plots, and we've got 8,000 something channels, it's going to get really messy really quickly. So instead we do these raster plots to look at data like I was showing in the lecture. So here we've got this plot space-time function that lets you choose what's your data array, what's your start and end time, what's your range of channels you want to look at, is there a title you want, and what's your sample rate. So just some basic information to create a plot. And so when we plot this earthquake during over just a range of channels, so this is going to go over channel 0 up to all of my channels basically, and going through all of the time in this 30-second file, we're able to see 30 seconds across all channels. And suddenly that arrival is just clear as day. When is that earthquake coming? So even if we were on these loud channels, we would be able to look over at some of the other channels, and at least we could still know that's when the earthquake showed up. Not showed up, but hit the array. And we might just want to zoom in on little parts of this. So part of what you're going to be doing in the exercises is just zooming in on just certain portions of the array. So let's say I looked at channels 5,000 to 6,000, so just over in this area. And I just wanted to look at the time around when the earthquake is arriving. So I'm just going to go like 15 to 18 seconds. And I could zoom in on different portions of it. And with that, I can see a lot more detail about how that earthquake is actually showing up. So when it's actually showing up, you see a lot of these arrival times are influenced by the sort of zigzag shapes of the array. And so you get earlier times, later times from a farther away point, earlier times again from a nearby point. So you see this kind of back and forth throughout the array. We can do this over a larger region. So let's say I wanted to look at like channel 1,000 to 6,000. Zoomed in on when the earthquake arrives, and we see there's a lot of this kind of back and forth in time. So you can play around with like which parts you want to look at there. And you can choose, which are the parts that you want to ignore, and sort of mask out those pieces. You can choose which channels do you want to ignore if you want to have any kind of array-wide sort of metrics of, this is when my earthquake arrives. If you want to do some kind of STA, LTA on certain metrics that you're calculating, then you could sort of zoom in, figure out which channels to mute out, to ignore, and then figure out which ones you want to include in that calculation. All right. So we might also want to visualize this just on the array itself. So here's just a function to sort of look at a snapshot of your DAS array. It's basically creating a scatter plot of colored markers where those colors indicate what your strain rate is at each location. And then you're actually going to plot like what's your data on top of the array location. So if you're having trouble seeing like where is the array kind of zooming, sort of getting hit first, earlier or later, or how is the wave kind of progressing over time, this can be really helpful for doing that. So you can change like what time you're looking at. You might think about, how do I modify this? Let's say if you just want to zoom in on a subset of the array, maybe just one little zigzag. How can you modify this code so that you can start to look at just little portions of the array to start to analyze where you might have maybe local scatterers? So like we talked about during the lecture, because we have sort of that spatial derivative being taken in DAS data, it's much more sensitive to local scatterers. We're sort of making everything look spatially a bit ringier. And so we kind of see those features a bit more. It's just like boosting up high frequency noise, sort of. Or at least it's analogous to boosting up high frequency noise. All right, so say I go to like 19 seconds. All right, so we can see at different times how that's kind of moving across the array. And the other notebook that has a link in here up at the very top is looking at vibrasize data from a source that's right around here. And so if you go into that notebook and try to run it, you'll actually see where there's a vibrasize truck going off, setting off vibrations, and you can see the wave kind of emanating out from that vibrasize truck as another sort of example of the types of things you can look at with this code. Right.
interrupt. We have a quick question in the Q&A, and one of the attendees has heard that DAS technology can be used to detect smuggling between national borders, and they're wondering if this is a myth or if this is real.
So this is something that like DAS, so a lot of the fiber optic technology was developed in sort of the defense space over the last few decades before it was even brought into geophysics. So like I mentioned, sort of things like pipeline monitoring or infrastructure monitoring, things like that. So this is part of what the sort of potential applications are. I don't personally work on this, and so I can't really comment on things like smuggling. I would think that most smuggling would not be detected this way. The one thing that I've heard people do work on is sort of tunneling detection under borders or facilities. And so with that, it would be either looking for sort of scraping sounds or you know, the actual noise of the underground construction itself, or it would be imaging. And so that is not a space I work in personally, but it's something that people are really working in. I don't know the level of success. You know, people that work in that space don't generally like to reveal details of what technology is or is not working. And so I don't actually know how successful it is, but yeah.
Thanks.
All right. Cool. So a lot of what we do with our DAS data, a lot of our processing is done actually in the frequency domain. So for instance, like I work a lot with ambient noise interferometry, and oftentimes it's faster for us to do our analysis in the frequency domain than in the time domains. Also, when I'm looking at, say, a new data set and I'm trying to get a feel for what's the seismic noise distribution, I oftentimes like to look at that sort of spectral analysis. You know, I also showed some examples of earthquake detection where it's easier to see whether an earthquake is happening if it's small, if it's kind of done in the frequency domain instead of the time domain. So we always want to be able to work with our spectral analysis. So let's say that I want to look at just one channel spectrum. We can use this code that I've provided here, and it's just showing an example of using the fast Fourier transform on a matrix, on a single trace here. So, okay, we can go ahead and plot that and look at our spectrum sort of before the earthquake happens. So here, or sorry, over the whole 30-second window. And we can change around which channel we're looking at. We can go to like, I don't know, channel 300 instead. Okay. And we can also look at what is it sort of before and after the earthquake to see if we just look at certain parts of our time, you know, how does that spectrum change? So again, it's just looking at single traces at a time. And we see this huge change in our spectrum before and after the earthquake has started. So I just kind of took up through 15 seconds and then 15 to 30 seconds here. Okay, so really we probably want to look at not just a single channel, again, because we know that DAS tends to be kind of noisy and we've got thousands of channels we can analyze. Instead, we want to work with a whole array. And so again, we're going to use this SciPy's FFT pack Fourier transform, but we're going to be working with it on a whole matrix of data. So we're going to take a whole whole array with a subset of time that we care about and a subset of channels that we care about. And then we just have to specify our axis so that it lines up with our time axis. And then it's going to let us do our spectral analysis there. And so if you haven't worked with that FFT pack before for working with matrices, that's what's going on here. That's kind of the meat of what's useful in here. Everything else is just error checking, making sure we've got the right Nyquist sample rates taken care of, all of that good stuff. And then we can actually make a plot. So let's say that I want to look at maybe 0.5 hertz up to 200 hertz and just 17 to 21 seconds. So right around the time that my earthquake is arriving, or right after my earthquake has arrived. I'm just going to look at channel 500 to 2000. I don't necessarily need to use the whole array, but I do want to get the power of some array. I don't want to just do a single channel. So let's take a look at its spectrum. Okay. And we can start to look at like, what was this spectrum like before the earthquake started? So let's say like 7 to 11 seconds. The earthquake arrived somewhere around 15, 16 seconds. All right, so there was our spectrum before. And so we look at each one of our channels has its own spectrum plotted there. So it's kind of a heat map. And Now let's go back to where we've got our earthquake that's happened. So let's say I'm at like, I don't know, 20 to 21 seconds, or maybe 20 to 22 seconds, just, all right. And we see a lot more of this like coherent energy in the low frequency bands, but also some broadband energy here. And so we can start to see like which channels are responding more strongly or less strongly to this event. I see a question in the Q&A. So does the frequency spectrum average the time axis across all channels? So here, we're just looking at each channel individually. So when I call that FFT function and I specify an axis up here we go. That's basically saying, take each one of these channels, take each of the columns of the data, and then take the Fourier transform in 1D of just that column of the data. So this is basically every single channel has its own spectrum that's calculated. There's another kind of analysis, which I showed in the lecture slides, it's called an FK. And with that, you're looking at a Fourier transform in the time domain, and then you do a Fourier transform in the space domain, and then suddenly you've got sort of frequencies getting mixed across different channels. So I hope that kind of answers that question. One of the other things that I showed in the lecture was that example of detecting a very small earthquake that Sioan Yuan and I had done. And with that, we were looking at across a group of channels, what's the spectrum for each one of those channels, or what's the amplitude spectrum for it? And each one of those channels has its own amplitude spectrum. And then we said, okay, for each one of these frequencies, we're going to average over all of our channels to see what's the average spectrum over those. And so that was a way of preserving our high frequency information. Since it was a small nearby earthquake, we needed that high frequency. But we still were able to get the power of the array by kind of averaging after calculating our amplitude spectrums. So that let us kind of know how much energy is in certain frequency bands. And that's different than averaging your time domain signal before taking a Fourier transform and then calculating those amplitudes. So that absolute value in there is not a linear operator. So yeah, hopefully that answers the question. All right, so I've got some exercises down below. They kind of range from what are sort of the easier getting started ones down to some stuff that's a little bit harder. So I'll just kind of go through what you can work on. I'll be on the Slack channel this week. I'll be checking it at least once a day or so. And so if you have questions as you work through these, let me know. And I can also post some solutions to these as well. So first, just check out like different visualizations of the array. Get used to the data, get comfortable with it. Find a few key channels, like some of the corners of the array or some areas that are really noisy, and just try zooming in on some of those. And then once you get comfortable with where are the different parts of the data being acquired and like, what does this look like? Try to identify if the earthquake is coming from directly above or if it hits some areas earlier than others, and if there's any apparent direction, and think about what could be causing what you're seeing. All right, so the next exercise is kind of to look at just the geometry of channels 200 through 700. This is along like where there's kind of a corner on the array. And look at it while the earthquake is arriving, like in that kind of early part of the time. And see if there's anything you notice about the data, and specifically like how the waveforms change across multiple channels in that area. And think about like what causes the data actually have some of these characteristics. And also think about whether you can like write some code to sort of automatically detect similar behavior in other parts of the data. So if you were to be given just here's a chunk of data that was recorded during an earthquake, figure out whether you're getting a certain behavior, then how can you do that? That's something that's actually like, this is the kind of thing that would be really useful if you have some dark fiber array and you don't really know what the geometry is, and you're trying to figure out, is this geometry similar to a corner? So something to think about. All right, and number 3, it's asking about, like if we want to use DAS data, it's better to use a bunch of channels than just a single channel, and especially for kind of those small amplitude earthquakes, that's true. So can you kind of modify that whole array spectrum calculation to return the actual spectrum as a matrix, in addition to just doing the plot? And then also think about, okay, once you've got that output matrix, how can you actually sort of quantify what the change in frequency content or distribution is? Like there's different ways you can do this. This doesn't have just one answer, but think about how would you quantify that? and try to write a function to sort of automatically calculate how that is happening so that maybe you could use that as a potential indicator of whether an earthquake is occurring. And you might also think about how consistent is that way of quantifying your change in frequency content before and after? How consistent is that across the different parts of the array? Or is it something that only kind of happens on one part of the array? And do you need to modify your way of measuring it if you look at other parts of the array? Something that's also just kind of a general skill for working with DAS data is being able to piece together a bunch of matrices of DAS data where they're each a bunch of channels and just a short subset of time. And then you got to take the same channels and the next subset of time. So being able to kind of do that gluing of your data arrays, this is just a practice on getting used to that. And once you think you've got your two arrays glued together properly, make sure that you're able to visualize the data right at that point where you're kind of gluing your two files together or stitching them together, and make sure that it actually looks like coherent waveforms moving across, that there's no interruption or anything like that. And okay, this is a big challenge exercise, but I thought it would be fun for some of you. If you check out this link, there's also nodal data, so seismic nodes that were recorded at the same site at the same time. So these are SAC format. I know you all have been working with OBSPy, and or I think they're SAC, maybe they're mini-seed. Now I'm wondering, because it's been a little while since I looked at those nodal data. I think they're SAC. Anyways, they can be read with OBSPy. And so if you can find two nodes that are kind of near each other and also near a section of the fiber that's parallel to those two nodes, can you start to do like things like maybe differencing their inline directions so that you can approximate what the DAS data should be like there? And can you compare that to the DAS data and how similar are they? You'll have to kind of rotate them into a certain direction. But also check out this paper if you want some hints on getting started with that node data and doing some of those comparisons. This paper was by Martijn van den End and is just really good use of this open Brady Hot Springs data. I see there's a question in the chat about some of the main challenges of DAS data. And I think that especially on data limitations, one of the biggest things is really understanding first, you have to figure out what is your data format, make sure that you understand that correctly. And so that's a lot of working with the team in the field, or if you're collecting data yourself, being really meticulous about how you're recording your data, since there aren't those totally standard data formats yet for DAS. I think that another thing that's really big is make sure that you just understand what does your data look like? Look at it in the time domain, look at it in the frequency domain, do a little beamforming, get a feel for it, because especially with a DAS array that has such a broadband response, it's really easy to be sensitive to very local noises, more so than say with a broadband seismometer or long period seismometer. So that's another challenge. On the data management side, definitely you don't want to be just taking like some external hard drive, or you don't want to be pulling a lot of data off of online if you can avoid it. If you can have your compute system really close to where you're actually storing your data, that's ideal. So if you have a high performance computing cluster at your university, or if you're able to maybe get like a student account on one of the NSF Exceed machines, you can start to learn about those file systems. How fast is it to access each different part of the file system? And you may be able to work with the computational scientists at that computer cluster to really figure out an optimized sort of way of storing the data, transferring it to a fast to access region, and then operating on it. So I think those are kind of the big limitations for now. A lot of time is just spent on reading and writing, mostly reading your data when you're doing analysis. So yeah. I see there's another question about how much is a DAS array with some maybe 5 kilometers of length. So I'll say like it depends on if you're using sort of specialty fibers or pretty standard ones, but I would say a typical cost for fiber optics is somewhere between like $1 a meter and $5 a meter if it's kind of a high-end one. It can vary. There are some that are much more expensive, and there are some that are a little less. But so that would put you somewhere in the like sort of $5,000 to $10,000 range for something like a 5 kilometer array. sometimes more than that, 15,000. It really depends on what your needs are in your experiment. Yeah. But then, of course, that's not including the interrogator itself. That's your big startup cost. And it depends on whether you're renting or buying, or if you have access to like a free loan or something like that, then it totally changes the calculus of how much an experiment takes to actually carry out. Yeah. Any other questions people have? Hopefully these questions aren't too open-ended that I've put up here as exercises, but like I said, I'll be on the Slack this week. Happy to like clarify questions. Some of them are sort of intentionally open-ended, so I can like brainstorm with people about, if you start trying something and you're like, what else can I do on this? I can help kind of point you in some directions too. So yeah.
Great. Well, thanks so much for that wonderful lecture. Oh, we have one more question. Are
great.
DAS can DAS be used to record, or are they effective at recording volcanic signals?
Oh yeah. So there are people working on DAS for volcanology studies. I think that Vladi Krakowicz and Philippe Jousset over in Europe, I think that they have some experiments working with volcano data. And there are several other groups that are doing things. So like Sarah Clausen over in Switzerland, I think that she's doing some stuff with Mount Meeker that's sort of volcano data. So it's certainly sensitive to some kinds of vibration. I'm not sure, like without having a lot of volcanology background myself, I'm not sure if there's a wide range of different signals where it may be sensitive to some and not others, but I would think that anything that's within that kind of frequency band of what DAS is sensitive to should be okay. So yeah.
Great. Well, yeah, thank you all for attending the live session for Unit 4. So we encourage all of you to work on the lab and discuss any issues or questions you have in the Unit 4 Slack channel. And yeah, Professor Meyer will be able to answer general questions you have with the notebook and with tests in general. Thanks so much again.
Great. Thanks for having me.
Yeah, and we'll upload today's lecture within around 24 hours, and we'll have a survey out soon for all of you to confirm your attendance and participation. And I guess if there's no other questions, we'll probably end the recording here. So see you all next week for a session on pi, GMT, and mapping. And thanks again, Professor Meyer.